Hi, this is the Data Science Barcelona podcast. We try to interview people who's doing interesting things in data science and some connection to Barcelona. Today we're interviewing Alejandro de Miquel. He's a colleague of mine in an enterprise called Genomerics, and we also coincided in mathematics and physics. And well, he finished second in the Kaggle challenge of abstraction and recognition. Sorry, reasoning. Well, that's great. So we will structure this interview because it's a little different. First, focusing on the challenge, and then going on with the more typical questions that I ask in this podcast. So I would ask you first to explain in terms of the W questions, what is this challenge? When, who, why, what?
Sure. As you said, I finished second in the abstraction and reasoning challenge. It was a Kaggle challenge hosted by François Chollet, who is the creator of Keras, this Python library for developing deep learning algorithms. The competition took place between February and May, I think, of this year, 2020. And it consisted of developing an algorithm capable of solving tasks that it had never seen before. And the tasks were similar to what you would see in a typical IQ test. Basically, the tasks consists of grid, input, output, input, output, input, output as an example. And then the solution that you need to give is given an input that is very similar to the inputs that you have seen, give the corresponding output. Okay. I will show a couple of examples. Maybe now I can share the screen.
Yes.
Let me. You can see the screen, right?
Yes.
So this is a blog post that I wrote, and I have some images, examples of the tasks, right? So for example, you see here task demonstration. No, here in the left, you see the input matrix with a shape, and then like with this blue and red shape, and then the output implies replicating the shape given the red dots that that are not part of the initial blue shape, right? Visually, you can see very clearly what needs to be done, in this particular task. And given the test input grid, you would be able to give a test output grid very easily, you as a human being. It's very intuitive what to do.
Well, I need some time, but
yeah, no, sure. No. Maybe it takes you, I don't know, like 5, 10, 20 seconds, in order to understand what needs to be done in the task. And other tasks are very similar, like the second task that you see is about recognizing the pattern that is repeated and rotated, whatever, but you always see that it's a 2x2 matrix, the output or the pattern, right? And eventually you will find the solution. In the third example, it's fairly easy to see which one the output is more or less quickly. So all these tasks have in common that we humans can solve them more or less easily, as said. How there is no algorithm currently that is capable of solving this sort of tasks that are so diverse between each other, but the reasoning behind them is more or less similar, meaning that you only need to take into account, like shapes and colors, maybe symmetries, And that's it. They are concepts that for us are very intuitive, right? However, nobody has focused on trying to develop algorithms that solve these sort of tasks. And this all belongs to a field that is more or less recent called artificial general intelligence. And there are still things that need to be investigated yet in order to build algorithms that are meaningful in a way. Anyway, so this was the setup. We were given 800 different tasks so that we could use them for training or as examples or whatever we wanted. And the leaderboard was determined by a set of 100 test tasks that were hidden. They are still hidden because even though the competition has finished, they still want to keep the test tasks hidden in case they want to organize something else in the future. And yeah, basically whoever solved the most number of tasks in the test set would win the competition, no? Basically, one task solved means 1 point, roughly. And by solved, it means giving the exact output, like the exact shape of the matrix, and every single pixel needs to be of the correct color. If you get 1 pixel wrong, the task is considered as not solved. And moreover, for every task, you could give 3 different possibilities as possible outputs, right? So you have 3 chances per task. So yeah, this is the setup, and yeah, I hope it's you understood what the competition was about.
Yeah, so let's say it's about measuring intelligence through a benchmark. Maybe.
Yeah. Here are some other examples. Well, there are many examples. As I said, there are like 800 examples, and later I will share with you like both the Kaggle website competition and maybe some of the other resources where you can see all the different tasks and so on. I will stop sharing my screen now.
Okay.
Yeah.
Well, they're interesting, these examples. Perhaps you can explain a bit what they try to encode. The article that supports this challenge by François Chollet speaks extendedly about what is intelligence and what not, right? What's your definition of intelligence, you would say?
I would say that, I mean, there are many different definitions of intelligence, right? And intelligence can be applied to many different faculties, or characteristics or capabilities, of humans. In particular, in this particular case, I would say that intelligence is the capability of basically performing a task that you have never seen before, right? Probably based on your previous experiences and learnings, making your own deductions in order to solve whatever task you are facing in an efficient way.
Yes, now that you mention it, I remember he speaks about you use some data in order to train, and also some priors, like core knowledges that you have. How do you code these prior knowledges?
I said before, when looking at the tasks, that they were intuitive for us. These core knowledge priors are, I think that they are things that would need to be encoded in a potential algorithm that solves this kind of tasks in order to mimic what is intuitive for us. Because, you know, when I say, yeah, this is intuitive for us, you know, what does it exactly mean? You know, like why certain tasks are intuitive for us, you know, which features do they have? I think that it's very important to be capable of understand the abstractions that we find intuitive, right? We find symmetries intuitive.
Okay, symmetries.
We find so if there is a certain shape, you know, like pixels of a same color that form a same shape, like a square or a rectangle of certain dimensions or a cross or whatever, we identify this shape as an object automatically. Whereas for a computer program, you know, that just sees pixels, you know, numbers, I mean, it's not obvious that a set of pixels that have the same color has to correspond to a same shape. There were many tasks in which you had a grid, you know, like a color basically represented a grid, you know, with several vertical and horizontal lines, you know, and for us it's very obvious, you know, that you had a grid, and if moreover all of the cells of the grid were of the same shape, there were a set of operations that, or of transformations that for us are intuitive, you know, like find the cell with with the biggest number of blue pixels, or I don't know, perform some kind of pixel-wise AND operation or pixel-wise OR operation, or I don't know. So the important thing, I think, is this, you know, like to try to understand what it means intuitiveness, you know, for us, what is intuitive for us, and translate this somehow to a computer program. Because, you know, given a random task like the ones that I showed you before, for us there is only one solution. But I'm completely sure that you could find out, and I mean, a lot of different transformations that give to many different outputs, and that they are all valid, you know, they are just functions, you know, that are valid for these three examples, and they generate many different examples, but only one is correct. Which one? The one that is intuitive for us.
That's a problem of the IQ test, in my opinion. But you know, that's what you're thinking about, and there's not another pattern that the designer didn't think of. I don't know.
Yeah, I mean, in this particular competition, there were some tasks that had, for us, intuitively speaking, 2 or even 3 different solutions that were valid. I think that this is why you were given 3 different options of the final output.
Okay, that makes sense, because at the beginning I was a bit shocked that you had like three chances. Like, why is it right or is it wrong? I mean, you had the solution or not?
No, it was because the final solution was not always unique. So,
yeah, but that has to do a little bit with generalization power. If you translate it into machine learning terms, you have training and test, and you may find a solution that works for train, but then you move to test, and if you overfit, it doesn't translate. This is a bit different because it's more logical steps, right? But I don't know, just me talking. Do you want to go into the algorithm? Walk us through the algorithm.
Yeah, the one that I developed, no, the one that we developed.
Yes.
Yeah, sure. I mean, first of all, I mean, I said that I finished second in the competition, but it was like my team, no. I developed this algorithm together with a friend of mine, Roderick, and then moreover, during the last 2 weeks, another competitor joined us who helped us solve a bunch of extra tasks, and helped us reach the second position. But yeah, about the algorithm. So the algorithm is not just a neural network or whatever. In fact, it doesn't use almost anything of what we know nowadays as deep learning or machine learning algorithms, sort of. So it consists of the following. Whenever we see a task, the algorithm does a lot of preprocessing in order to understand the basic concepts of the task, like, so if a task consists of 4 training samples and 1 test sample, then the preprocessing step would be, okay, what do the 4 test samples have in common? Are the shapes of the matrices always the same? Is the shape of the input matrix always the same as the shape of the output matrix?
Yeah, it's not a fixed shape. It's more difficult.
Yeah, I mean, the shapes could be from 1 to 1 pixel to until 30 times 30, right? So it's very variable, and it doesn't necessarily have to be the same shape, between input and output or between samples. So there's one of the things that you have to look at. Which colors are there in each sample? Which colors never change? Which shapes appear within each sample or within each matrix? Whether there is any kind of symmetry, whether there is any kind of grid, and so on. So we would list a sort of properties, of every matrix, of every sample, and of the task in general. Also identifying the background color, things like that. And then the next step would be, okay, given these properties of this particular task, we had a pool of different operations, basic operations to be performed to the input matrices in order to transform them to some output matrices, right? So for example, I don't know, like move the red pixels 1 square to the right, or change all the blue pixels into green, or paint the biggest shape with gray color, things like that. So out of this huge pool of operations, of basic transformations that we had written, given the properties of the task, we would choose the set of operations that would make sense to try on the input matrices. We would apply all these operations to the input matrices, and we would obtain output matrices. And then we would compute a score for each and every operation, depending on the number of pixels that were correct in the output matrices. And after applying all these operations, we would select the operations that contributed positively to the final solution. This is if an operation made our final output matrices be closer to the real output matrices, meaning that the number of incorrect pixels was smaller, basically, then we would consider an operation as good, right? And what we would do if we consider an operation as a good operation is, okay, given the output matrices that were generated by this operation, we would again analyze the whole task and concatenate another operation after this first operation, and then evaluate the concatenation of these 2 operations. And we would do so until we found a solution of the task, meaning that the number of incorrect pixels of the output matrices would be 0 incorrect pixels. And at this point, we were only using the input matrices for evaluating this. And once we had this concatenation of operations, we would use this concatenation of operations as our final solution, and we would apply them to the input matrix of the test sample, and the resulting output matrix would be our final result.
Okay, so you keep adding functions to your list until you reach a solution.
Yeah, that's it.
Yeah. And you discard the ones that work worse.
Yes, yes. If applying an operation leads to no improvement, then I discard it completely.
Yeah. Okay. Like, how do you manage the candidates or proposals? How many do you work with? Or
so, as I said before, you could, for every task, you could submit up to 3 different candidates, right? So I would keep track of my 3 best candidates. I would rank the candidates according to the number of incorrect pixels in all of the output matrices. You know, the sum of incorrect pixels in all of the output matrices of the different samples. And then I would keep track of the 3 best candidates. And then if after applying another operation, I would get a set of output matrices with a better score than any of my 3 best candidates, then I would substitute the candidate, you know, my new candidate by the worst of the 3 candidates that I had before.
And then you move on the next ones.
Yeah.
You don't keep going with the same, right? That doesn't make sense. Yeah.
Yeah.
Could you explain more about the preprocessing that you mentioned? First, some examples. You said some about the information that you gather from the matrices, but yeah, maybe something more complete.
Yeah, sure. So I mean, give me a second. You know what? I actually have all my code on GitHub. I will share it with you later. But if that's okay with you, you know, I will just have a look at the GitHub code, you know, because I really, you know, have a list of all the properties, you know, that I looked at, you know, and it would be nice, you know, I think maybe just to give you
examples.
Some examples, right? So right now I'm looking at the file where I defined the properties of the different objects, right? I generated classes that were called, you know, like matrix, task, sample, grid, you know, and so on to store basically the properties at every level, right?
You know what we can do?
Yeah,
I just came up with this. There's this idea that I tried to start to explain about the prior knowledges that could be classified into 4 groups, like objectedness, like segmenting entities. The other one is sizing or counting, big versus small, and frequent versus rare. And then there's agentness, like realizing that some entities have goals, like can chase another or can connect to others. And the other one was, I think, geometric, like kind of the shapes, things that you mentioned, like inside or outside or invariant to rotations. We could try to classify into those 4 categories, the examples.
Well,
too much.
Okay. Okay. You see some file now, no?
Yes, class task.
So yeah, in this file I defined basically all of the properties, you know, of every task and every matrix and every sample, right? And this was all part of the preprocessing, right? So as said, I created a class task, that would look at properties that were general of the whole task, right? So, I would look at the number of train samples, number of test samples, the shapes of the matrix, whether the input matrix had always the same shape, whether the output matrix had always the same shape, whether the input and output matrices would have always the same shape, if the matrices were squared, if there was a factor between the input matrix and the output matrix, these are always things, that relate just to the shape of the matrices, like the number of n times m pixel, of each matrix. But in the end, it's important, because one of the first things that you need to find out is, okay, if you're going to give an output, what is the shape of the matrix of the final output? Which is not always obvious.
Size matters.
Size matters, yeah.
Sorry, let's go.
And I would look at whether the matrices were symmetric, like the output matrices, basically, if they were symmetric.
Okay, symmetries. So
I
shapes, geometry.
Yeah, that goes later, I would check at the colors, the number of colors, which colors are there, both in the input matrices and in the output matrices. There was this very useful thing called fixed colors, which means that if there is if the input and output matrices had always the same shape, then maybe some colors, they didn't change between input and output. If a pixel was red in the input matrix, then it will be red in the output matrix as well, and this
I'm not following, sorry. Like, what's the reasoning?
Yeah, so imagine that you have a task in which the input matrix and the output matrix have always the same shape.
Yeah.
N times m, n times m, for example, right? Then you can map each pixel. You can do a one-to-one mapping, of each pixel.
Okay.
The output matrix, right? Meaning that, okay, maybe this pixel, the pixel 1, 1 in the input matrix is red, implies that the pixel 1, 1 in the output matrix is red as well. You can do this one-on-one matrix, and you can find the fixed pixels, or fixed colors, colors that will not change between the input and the output.
Okay. So pixels that don't change color.
Yeah.
Okay.
Yeah. And this is important, because sometimes this sort of pixels would represent a grid. Sometimes this sort of pixels would also represent, would also tell you whether there has to be a rotation or not, for example. There are some cases in which there was a horizontal or vertical bar of a specific color, right? That would determine whether you should interpret the matrix vertically or horizontally, right? And then it would be useful as part of the preprocessing to do some rotations consequently. Like, for example, I remember a case in which basically there was a red bar that would mark some sort of gravity, and all the colors, all the shapes would fall on the red bar,
Okay.
But sometimes the red bar would be vertical, sometimes horizontal, sometimes at the top, sometimes at the bottom, and in this sort of cases, it was useful, to just rotate the matrix and consider that the bar was always at the bottom, for example,
Mm-hmm.
And then it's just, okay, it's normal gravity, the objects are falling, that's it,
Yeah.
Then, I would have a look at the different shapes. Here, the naming is a bit confusing because I say the shape of a matrix and also shapes within matrices. It's different, with shapes within matrices, I mean like objects that we see visually.
Okay, yeah, it's no problem.
Yeah, so you could have a look at the different shapes that were within the matrices, if there were any common shapes between input and output, whether there was a grid. You had to check for the background color, if the background color was always the same in every different sample of a task.
How did you determine the background, or if there was any, for example?
Basically, I will look at the color that was predominant.
Yeah. So if it's disconnected, it can still be.
Yes.
Like a chessboard, like, yeah, I don't know.
A chessboard, I don't know. It's the same number of pixels, both black and white, So that's.
I mean, I'm saying this kind of things because I think Chollet would go for the tricky things, maybe.
Yeah. No. In this case, I would probably consider that there is no background color, and even if I decide that there is a background color, it's just one more factor in that plays a role in the final functions that I want to use. Even if the background color is not correct, it doesn't mean that in the end I won't choose the right function,
Right.
Because I will try so many functions, Some of the functions that I try will not take into account this background color, They will be like, yeah, whatever. Just move all the red pixels to the left, independently of the background color. So yeah, following patterns and many things, and this is only at a task level, and you saw that, okay, this file has 1,600 rows, and basically all of them are just properties, class task. Okay, so you see you have like 400 rows, basically listing different properties of the task as a whole. Mm-hmm. Then I also listed properties of, at a sample level, many of them. I listed properties at a matrix level.
What's the difference when you say sample? Is it input-output, right? And
yes, a sample is a pair input-output, yes.
Okay. Yeah, of course.
Yes.
So you start with matrix and then build up into samples and tasks.
Yeah, well, and you could even go further, and after the matrix, what is the next level? The different shapes that are in every matrix. I know, class shape, right? You will look at the number of pixels of the shape, of the color of the shape, or of the different colors of the shape. Maybe some shapes, they are multicolor, whether the shape was symmetric or not, if it's a rectangle, if it has any subshapes, many things.
Oh, yeah, it's a lot.
Yeah.
An equal, so you had to define an equal, sorry.
Yeah, sure.
Okay.
Defining equality of shapes, yeah.
Okay, go on.
Yeah. And other functions and stuff, yeah.
Subshape, wow, yeah.
No, it's a proper program, that we developed.
It looks well written, yes.
Thank you. Yeah. Anyways, I will share the GitHub repository with you. You see, I explain a bit what the algorithm is about, and the list of functions that we developed. That's also useful.
Yeah, we covered now a bit the information preprocessing.
Yeah.
And then the next step is choosing which you call functions.
Yeah,
you apply.
Functions, whatever. Yeah.
And how do you go about that? Choosing what makes sense?
So, I mean, again, it depends on the properties that I find during the preprocessing, right? For example, if I detect that the output matrices have always the colors green and red only, then I would not consider any transformations that imply having blue in the output matrix, right?
Right.
If I see that the output shape of the matrix is always the same, I will only consider transformations that imply having this output shape, right?
Yeah.
This sort of things.
So yeah, and in the other case, if it's a different shape.
If it's a different shape, then I would not consider transformations that imply having the same shape, no? And then I would, I don't know, try different things. Maybe look at the count of colors, you know, or maybe the output shape is a factor of the input shape, right? Maybe if the input matrix is like 12 times 12, the output matrix is like 4 times 4, for example, like divided by 3, right? You know, and then if in the next sample, if the input matrix is 15 times 15, you know that the output matrix will be like 5 times 5, right? And then you would try operations consequently, right? You would, I don't know, choose a subset of the matrix, or I don't know, you would count the different number of colors and do something about it. I don't know. Many different things that you can, there are many different things that you can try always.
Yeah, there's lots of things. So you have like a logical program. If this, then these ones make sense. It's not that.
Basically, yes. Basically, yes. If I have these properties, try this operation. If I have these properties, try this operation. And that's it.
Yeah, like your examples based on size are pretty sensible. You said color too. I don't know what else there is. Patterns, right? You work a lot with patterns. Or...
yeah, or again, symmetries, you know, if I know that the output matrix has to be symmetric, then I would force to choose a function that whose output is symmetric, for example.
Okay. So yeah, I guess we're going quick. The next step would be the functions. Can we see some examples too, as well as we did with the properties?
Yeah, of course. Of course. I'll share the screen again. So, okay, this is a list of functions, you know, with the name you don't understand that much, you know, sometimes. You see that there are some deep learning or neural network related functions, you know, like CNN or LSTM, you know, I would train like very tiny models in particular tasks to see if that helped. And in some cases, it helps to train a small CNN model or an LSTM model. But you need to understand what these sort of functions do, you know, in order to understand in which cases it can help. In some cases, the name of the function tells you a lot about what it does already.
Why CNN or why LSTM? How do LSTM help?
LSTMs are good for sequences, right? So in some cases, there was some sort of sequence encoded in the matrix, right? You would have a matrix with different objects or shapes, right? And in the output, these shapes would be the same ones, for example, but following a specific coloring order, you know? They would be always like, the first shape is blue, the second shape is green, the third shape is red, the next one is blue, the next one is green, the next one is red, and so on, right? In the end, they would be like sequences. So training an LSTM at a shape level, at an object level, would help finding these sorts of sequences.
And how do you? Oh, sorry. Finish and then
Yeah,
I'll ask.
yeah, and then the CNNs, a convolutional neural network, would look, given a pixel, how the pixels around it look like, right? So, for
Neighborhood.
example, if I have a blue pixel, and then always in the output, on top of the blue pixel, there is a red pixel, and to the left of the blue pixel, there is a green pixel, then the CNN would detect it, and would do this transformation automatically. Maybe it's an overkill, because it's just looking at neighboring pixels and whatever, but it works, And it didn't take that much computation time because the networks were quite simple.
Yes, if you make them really few parameters.
Yeah.
And then, well, not then, back to the LSTM, the elements of the sequence can be a lot of things.
What do you mean? I always chose just particular shapes, particular objects in the matrix, right? And what I will decide is which color needs to be the color of the shape.
Okay.
Yeah, whatever. let me show you the where I chose the functions to be selected, the operations to be selected. It was in this matrix, in this file. So this function was quite important, this get possible operations. As I told you, once I did the preprocessing, I would look at the operations that made sense to try, right? So,
easy.
For example, I would, like, T and C are the task and the candidates, right? Given a task and a candidate, this function returns a list of all the possible operations that make sense applying to the input matrices of the candidate, right? And then I would just try different operations, like if in the task the input and the output had always the same shape, the input matrix had the same shape as the output matrix, then I would try different operations. Like, I don't know if they're like, I would apply a color map, if it made sense, I would try a color map, meaning like I turn all the red pixels into blue, all the blue pixels into green, all the green pixels into yellow, and so on, Yeah. And I would try the color maps that would make sense. Or I would turn the input matrix into something symmetric,
So
Or
remove small asymmetries or...
Yeah, remove asymmetries or whatever, yeah.
Yeah, symmetries, remove asymmetries.
Turning it into a left-right symmetric matrix, up-down symmetric matrix, or the diagonal symmetries or whatever.
Like you're assuming that it's mostly symmetric and then, or you mean like doubling? You mean replicating? No, same shape, right?
Yeah.
Okay. So changing a few pixels.
Changing a few pixels of the input matrix so that the final matrix is symmetric. Which pixels do I change? Well, that depends on the colors that I see are modified between the input and the output typically. If I see that there are always black pixels turning into something else, maybe that's what I will do, in order to turn the matrix symmetric. Just turn the black pixels into whatever is necessary in order to make the matrix symmetric.
Okay.
Complete
rectangles.
Complete rectangles.
Yeah.
If only some shapes need to be changed of the color, there are several different operations that I can try.
Complete rows.
Yeah.
Yeah, it's a
The
lot of
CNNs.
stuff.
But it's always this same kind of pattern, If the task is like that, then I try the mirror operation, Like, if in the task the input matrices and the output matrices have always the same color count, then I try to mirror the matrices, like basically flipping them, to right or up and down,
Okay, yeah, that's only two possibilities, but maybe some of these functions have like hyperparameters, like they are a family of functions.
Yes.
How do
Yes.
you choose?
I try all the parameters that make sense.
Okay.
You see, this is an example. Connect any pixels. This is a function that what it does is that if I have a blue pixel here and a blue pixel here, and no blue pixels in between, I try to make a line connecting them, right? And the line can be blue as well, or can be of any different color, right? So here you have the parameter connection color, right? This is the color of the pixels, the color that I use to connect these two pixels. Connection color is CC. And here I iterate over several colors that make sense to try, Basically,
change it out colors, yes.
Yeah. These are the colors that appear in all the output matrices, basically. Mm-hmm. And so on, there's just a lot of operations that I try, Some have cryptic names, some not so cryptic,
Logic gates.
Yeah.
Yeah.
Playing with grids. Yeah, there are just a lot of operations, that I try, always with the if it makes sense, try it, and so on. Yeah.
So did you code this mostly beforehand, or as you go finding new examples? Oh, this breaks my scheme, I had to add new things.
No, as you find new examples, you add new things. So in the end, what you want to do is to write functions that apply to as many tasks as possible, right? But the tasks, they are so different between each other, right? That whenever you see a new task, it's like, okay, how would I solve this task in particular? Which operations do I need in order to solve this particular task? And then you try to write it down, and that's basically it. What you want to do is, though, it's not only looking at one task and try to solve it, but looking at all the tasks and thinking of operations that could be potentially used for solving many tasks.
Yeah. General artificial intelligence.
Yes.
Yeah. So it's not machine learning, as you say.
Not really.
But it's artificial intelligence.
Yeah, some would say that this is some sort of genetic algorithm, right? Because in the end, you are just choosing three different candidates that you give us as solutions, right? And in the end, it is kind of learning from the input and output samples. So
yeah, but not in the continuous traditional approach, like fitting a
no,
continuous parameter.
no.
More like finding a sequence of functions.
Yeah, and the sequence of functions, I mean, the number of sequences of functions that I can generate is finite. So
Okay. So we covered preprocessing, transformations, the scoring, and managing the candidates. You speak about post-processing, what is that?
Yeah, so in some cases, the preprocessing implied performing some sort of operation or some sort of transformation to the task. I said previously an example of having to rotate the matrix, with the red bars that would determine the direction of the gravity, right? I would rotate the matrices, right? Then perform operations, and then as part of the post-processing, rotate them again to their original status, let's say.
Yeah, okay. So you had to keep in mind the transformation to undo it.
Yeah, exactly, yeah.
Okay, so now I would say, yes, we have done the walk through the algorithm pretty extensively. Yeah, some crazy transformation, perhaps. There are some machine learning ones, which you said make sense. Yeah, what's the craziest you have there?
The craziest transformation that I have.
Generate mosaic. What is this?
No, that's quite simple. That's if I saw that the output matrix was always bigger than the input matrix, let's say that the input matrix is 2 times 2 and the output matrix is 6 times 6, I would replicate the input matrices many times in the output matrix, but sometimes rotated, sometimes mirrored, and so on, and I would try to generate a mosaic using as an initial pattern the input matrix, just by copying this input matrix many times onto the output matrix, which has to be bigger.
Okay. Yeah, the other ones are pretty much evolve.
Yeah, that one maybe was a bit crazy. It didn't work very well. It did solve some tasks, but it was quite complicated what I tried to do with this evolve function. I tried to that's hard to explain. So starting from a pixel or a shape or a source in the input matrix, I would try to make it evolve according to what it saw in the environment, It's like sometimes the task would consider of, I don't know, for example, starting from a red pixel, moving it always down, like extending it always in the same direction until it found an obstacle. Let's say a blue pixel, and if it finds a blue pixel, then the line turns right. Then you turn right until it finds a green pixel, and then it turns down or left or right again or whatever, and so on. And so you make this line evolve slowly according to what it finds in the environment, in the rest of the matrix. Yeah, that's basically it, That can be applied to a line or to whatever shape. That doesn't have to be a line, it's something that needs to evolve and act in one way or another depending on the obstacles that it finds in the rest of the matrix.
That's for the agentness.
No.
Yeah. Okay.
Yeah. I tried to develop something like that because I saw several tasks that kind of follow this pattern, and I tried to do something as general as possible, but it was quite complicated.
Okay. Yeah, paint shape from border color. You work with border concepts, I guess.
Yeah. Yes. Sometimes, like a border would define, I don't know, a frame, and you only need to look inside the frame, or a border would tell you which shape to look at, which shape is the one that is important in order to decide something in the output matrix, like some color or whatever, Yeah.
So your approach to solve this was look at examples and incorporate.
Basically, yes.
Because you see, I'm pretty obsessed with the core knowledges of François Chollet. I don't know if you could reverse engineer it and put yourself in the mind of the guy and say, okay, which things do I want these tasks to measure or represent, and then try to describe the possible space of tasks. Do you think it's a finite space of unique tasks you can generate?
I mean, I think it's virtually infinite. I mean, it's obviously finite because the matrices, they have to be minimum 1 times 1 pixels and maximum 30 times 30 pixels, and you have only 10 colors to play with. So there is always a limited number of input and output pixels and colors and whatever, this is limited. So obviously it's finite, but the amount of different combinations and the amount of different ideas that you can think of is huge. It's huge, you can always think of a new different idea, that you have not thought before and that you can represent in such task. So I think that it's so complicated to find some program that learns or solves a task using a concept, a whole concept that it has never seen before, that I don't think that we are very close, of solving these sorts of problems yet.
Okay, so from the point of view of the solver, you're saying that's hard.
Yeah. From the point of view of an algorithm.
Yeah.
Right? An algorithm aimed at trying to solve this sort of tasks, tasks with concepts that the algorithm has never learned or never seen before or are not even encoded in the algorithm, How do you make an algorithm solve these tasks? Right now, all the deep learning algorithms, all the deep learning approaches, they are based on repeating a task that it has been trained for over and over again, with a lot of samples, but it's the same task all the time. Sure, the inputs are slightly different, but the task to be solved is always exactly the same.
Yeah. And does your algorithm learn something?
I mean, what does mean learning? It kind of learns which are the best operations to be transformed given a particular task by evaluating how good an operation is by the number of pixels that are incorrect, when you check the output matrices. That's kind of what it learns, but that's basically it.
What do you think the creator of this challenge expected the models to be like?
I don't know what to think. Probably I think that François Chollet, the creator of the challenge, he's very aware of that this is a very complicated problem to solve. And he probably threw it to the Kaggle community in order to see if some cool ideas came out. And I know that he didn't expect anything super special, super particular, because the competition lasted only 3 months, it's always individual people or teams of 5 at maximum, that can collaborate. So within only 3 months, on such reduced teams, it's not possible to develop something amazing, right? And this was shown by him already at the beginning of the competition, saying that there was an extra money prize for whoever solved more than 20% of the tasks in the test set. 20% with the algorithm. So if you solved over 20% of the tasks, you would get an extra money prize, and that was him basically saying, hey, this is something really complicated already, solving 20% of the tasks, right? And in the end, this is what happened. Only one person managed to solve over 20% of the task.
He knew.
Sorry?
He knew the other 80% were impossible already.
No, that's not it. In total, I think that like 50% of the tasks were solved by someone, by at least one team.
And when you merge teams, how did it change? Overlap.
Yeah, I think we had an overlap of 2 tasks that were commonly solved between our team, our extra team member and us. So he gave us, I think, like 5 or 6 extra tasks. That in the end is what helped us finishing in the 2nd position, Otherwise, we would have finished in the top 10 anyways, which is quite cool. But thanks to that, we finished 2nd.
And how did you incorporate the 2 projects?
So basically, you know that we used a system of scoring our different candidates, right? Our candidate would have a 0 score if all of the pixels are correct, right? So if we had a 0 score after performing all of our operations, there was a good chance that we were giving the correct solution, So whenever we had candidates with score equal to 0, we would give our solution. And whenever that was not the case, we would give solutions of our good friend, Yuhi.
So it's like bringing two participants and choosing the best. Okay, yeah, why not? I mean, that's the smart way. Yeah, I thought you would incorporate new functions and all, but no, you can just guess and evaluate.
I mean, we had only like 1 week to merge. Would have been too complicated.
No, it works. That's nice.
Yeah.
Can this be applied in general to Kaggle challenges?
Yeah, I think that the Kaggle, I mean, it was my first experiences in Kaggle challenges, and I think that this whole merging thing, it's a bit unfair.
It's part of...
These are the rules, so.
Yeah. Okay, but yeah, you still need to choose which one of the candidates to choose.
Yeah.
So you need some evaluation.
You need to give a solution, right? So. Yeah.
Well, you had 3.
You had 3, yeah.
So perhaps you didn't even have. You could take one, and the third random. Like,
Yeah. I mean, I said I would choose my candidates that would have a score of 0, you know. So
okay.
sometimes it was 1, sometimes it was 2, sometimes it was 3.
Excuse me.
In some tasks, I would have 1 candidate with score equal to 0. In some tasks, I would have 2 candidates with score equal to 0. And in some tasks, I would have 3 candidates with score equal to 0.
So it's true that there are different ways about solving an IQ task.
Yeah. I mean, you saw that I was using LSTM and CNNs, right? These are machine learning algorithms that, and if you consider that you only have 3, 4, 5 training samples, there is a risk of overfitting, let's say.
Yeah. The documentation, can you do that?
Yes, some people did that, but it's not obvious as of how to do data augmentation. I didn't go that way, really.
Yeah. Yeah, but perhaps to generate the new samples, you need to already program something that understands that.
Yeah,
So it's better
exactly.
to just program it. I don't know.
Exactly, yeah.
That's the problem with machine learning, that you have to understand the task in order to teach it, or you need examples.
Yeah.
What did you do you think solving these tasks or looking at these problems told you about your thinking process?
Sorry, again?
Yeah, I guess you had to reflect a lot on how you think and how you solve tasks as a human.
Yeah.
What did it teach you about this?
Well, I guess it reminded me of something that I've thought about many times already, which is that given a certain task, there are many different ways to solve it, right? And sure, like you can follow many different paths, you know, to get to the same solution. And applied in this particular problem, what this means is that there are many different kinds of operations that you can apply to a task in order to get to the correct solution, right? There is not only one way of operations to be concatenated, you know? Even though these tasks were very simple, relatively simple, the more I thought about each of the tasks, the higher the chances were of me finding out different ways of combining operations in order to solve every task, you know? In mathematics, you have the example of given a theorem, you maybe have many different ways of proving this theorem, you know? It's like very famous that, you know, the Pythagoras theorem can be proven in 300 or I don't know how many hundred different ways, you know? And you know, you can get very creative, really, as of how to solve one particular task, you know. And in the end, what is really powerful is not only being able to solve this task, you know, but being able to solve this task in a clever way, or in an efficient way, or in a way that is applicable to many other cases, you know?
The simplest.
In general, it's the simplest, yeah.
Okay, that's a nice thought. Many ways to roam.
Yeah.
So more about the philosophical aspect of it. I remember, I don't know if it says like that, but in the paper, it mentioned a quote saying that whenever a machine is able to solve a task, so for example, back in the 80s, or the programs, computer programs that could solve chess, or nowadays the machine learning algorithms that can solve certain cognitive tasks. Once a machine can do it, people deem this as not intelligent, because a machine can do it, you know. So
No,
it's false.
that's not correct, really. I mean, by now, I mean, again, machines are trained to solve very particular tasks, you know, like by now, you mentioned chess. By now, machines are much better than any chess player in the world. Does it mean that professional chess players are not intelligent when it comes to chess? I mean, because machines are better. No, I mean, it's not true, you know what I mean? They are very intelligent. But what happens is that there has been a lot of time, money, and effort spent in order to make an algorithm, in order to make a machine more clever than humans in that particular task.
Okay. Yeah, so it's not efficient.
No, it would be efficient maybe to make an algorithm capable of making algorithms.
Well, your approach is kind of general, in fact.
Yeah. I mean, this is why it's called artificial general intelligence. You know, like the goal is to solve, like to generate functions. You know, to generate algorithms capable of solving different kind of tasks. You know, and not only one particular task, which is what is done nowadays.
And what about conscience? Do you think you can call intelligent something that doesn't know it exists, so it doesn't know what it's doing? Or
I'm not sure what you mean by that. Because
I went really deep very fast.
Because, I mean, right now, algorithms, do they know they exist? No, I mean, they have no idea. They just work, right?
Yeah, so they don't know what they do if they don't know they exist. I don't know. Yeah, stupid question. Okay, let's move on. No, but there's a valid question of what's the line to draw when you say this is intelligent and this is not yet intelligent. Well, what's your line?
I mean, I'm not sure what to say, because I think that the word intelligence is applied with different meanings when it comes to algorithms than when it comes to humans, right? I think it's just something different. There are some common things, you know, like, yeah, sure, the ability of solving tasks it has never seen before, yeah, sure, or of learning, you know, to solve a certain task. But what we call intelligent algorithms, the intelligence that we refer to is very different to our intelligence, I think.
What other kinds of intelligence would you?
I don't know, all sorts of intelligence related to creativity, for example, or understanding people, or I don't know. Sure, right now there are generative algorithms, you know, that, I don't know, generate pieces of art, you know, but they are not really creative in a way that a human could be, you know. They are just replicating styles that already exist and have been invented by particular humans.
So creativity, not yet. or never?
Maybe someday, yeah.
Yeah, everyone is trying to figure out which cognitive abilities will survive the machines. Like, what will humans be useful for as machines keep getting better?
Yeah, I mean, I think that, I mean, I think it's obvious that the world is going to a more automated society in many different ways, you know, and I think that this is something good, you know, and the more things machines can do for us, the more free time we will have, you know, which is great, you know, to do whatever we want, and then we will have to find out, you know, ways of occupying our time, you know. So I don't know. I think that the way to automation in general of many things in society is very positive, right? So all good.
Yeah, well, but then there's less jobs, and it doesn't necessarily mean you get paid for not doing anything.
Well, probably as we get to this point, people should start getting paid for like just for not doing anything, you know, just a world general. What was the name? General income or something like that, you know?
Universal income.
Universal income, yeah.
You think
So,
that's what will happen?
yeah, I hope that this happens.
Yeah. Yes, but I don't think it will happen. I think a part of the population will lose their job and the technology replaces that, and they'll have to figure out some creative work that cannot be done by that technology. I don't
Yeah.
think the rest of the occupied population is going to say, yes, of course, the poor guy got replaced by a machine, let's pay his rent.
I think that machine replacing people is something good because it relieves of a job that a person has to do, you know, in order to survive. What needs to be done is to make an economic system that makes sense and is capable of sustaining everyone, even if they don't work, you know. Because otherwise, you're making people work without really the need or the necessity, you know, of these people working. So, I mean, that's I think that this is counterproductive.
Yeah,
For
totally.
for individual people.
Sorry?
I think that this is counterproductive for society and for individual people.
Yes, I mean, even nowadays, many of the jobs, it's like, come on, man, are we doing this? But at least until now, it's like people just work for money. Whatever gives money, they work. If it doesn't give money, they don't. Although we're going to bullshit jobs, like like I'm not saying they're not interesting, but I mean, yeah, I thought it was about getting food and clothes, you know, not these kind of things we're doing now, especially in data science. Like, I don't know, if you go to apply to jobs to London, for example, there's a whole lot of startups that are analyzing text data from all sorts of sources, and I wonder, like, is this really a business or necessary? Well, I don't know, I'm digressing, but yeah, I think we covered the point.
Yeah, no, I think that, yeah. Ideally, you know, jobs should have a purpose, right?
Yeah.
A purpose that is beneficial, that is meaningful, and ideally that is not about, ideally I would like jobs to not be focused on making money as the main goal, right? Because then it's easy to forget about everything else, and it can lead to decisions that are not very good from a moral point of view.
Yeah, totally. So if you have the choice, if you have enough money to choose, yeah, you should. So let's go into the more personal part of the interview. What do you value about a workplace, a job?
I value having challenges. I want to do things that are complex, that are complicated, and that I can that I feel, that okay, I'm applying in some way what I know, what I have learned, what I am capable of in order to do something that is complex and that's valuable and that's productive. I value that there is a purpose of my job, as said, that I'm doing something that in the end will be, I don't know, used by people or will help people in whatever way. I value having some freedom to do the job the way I want. I value to be given opportunities to learn, be it via time, be it via some material or whatever is necessary. And I value working with nice people in general, that you can have some nice conversations with, that will not have a bad word against you if you do something wrong, that are open to helping you whenever you need it, and so on. I think that, yeah, this set of aspects summarizes pretty well what I would want in a workplace.
Yeah, I think it's pretty common what you say. Yes. I feel the same way. Yes. Just before we move on to the second part of the interview, do you have any written notes about when you were developing the algorithm?
I do. Okay, let me see. So here, do you see something?
It's a lot of text.
Here I was analyzing what determined the final output shape of the matrices, all the different options. There were a lot. Yeah.
I expected more like drawings, and it's like really.
No drawings, it's a lot of writing. It's just writing all the time. Like writing, this is a list, an order list, 1, 2, 3, 4, 5, determining the how important one color is in a task, depending on whether it appears in the input matrix or the output matrix or both or whatever, because sometimes I would I would recolor the whole task depending on how important one color or another color is. So yeah, I made a list, of what are the features, the properties of the colors that are important.
Nice.
You see, list of tasks, that I solved and that I didn't, Like, I think that this is a list of tasks that I expected to solve using a particular function, right? And then I was keeping track, of which tasks
Incremental.
I actually solve with this particular function or not, And yeah, many things. Things like that. It's just, there are no drawings really. It's just writing and lists and stuff,
Yeah, I was expecting drawings and arrows and yeah, it's just.
Here there is a drawing.
Overlapping rectangles.
Rectangles, yeah.
Area of overlap or something.
Yeah. Yeah, but not much more really.
Yeah. So just from thought to code.
Yeah.
Yes?
Yeah, mostly, yeah. I mean, in total, there are maybe like, I don't know, 30 pages written with things in 3 months. So that's not a lot.
Yeah, that's pretty direct. Yes, to coding. Yeah. Yeah. So I guess we're done with a part of the challenge. Unless you want to comment something else.
No, that's good.
Yeah, I'm glad with what we did. So let's restart. Could you explain a bit about your background, education, relevant experience?
Yeah, sure. So I'm a mathematician and physicist. By education, I studied mathematics and physics at the University of Barcelona. Right after finishing my studies, I started working at this company called Geonumerics, which is the one that you were working at as well, Alex. Yeah. It's a company that develops software, I mean, navigation-related software, basically sensor fusion with input from GPS data, accelerometers, gyroscopes, images, and so on in order to either do mapping or knowing the location of vehicles or whatever, these sorts of things. So I spent 2 years working there. At the same time, I was also studying a master's degree in advanced mathematics, also at the University of Barcelona. And once I finished the master's degree, I quit my job, took a short break, and then I managed to join MathWorks. MathWorks is the company that develops MATLAB. And I was working there for about 1.5 years with the deep learning and GPU team. So I was there contributing in developing what is now the current framework for developing algorithms in MATLAB. And I quit my job in November last year, so almost 1 year ago. And I quit because I moved to New Zealand. You know, my wife, she got a very good research position here in New Zealand at the University of Otago, and I came here with her. And since then, since I'm here in New Zealand, I've been working on some personal projects, doing some freelancing, working as a contractor. I've been involved in many different projects, you know. And for the last, I mean, one of the things that I've done was the Kaggle challenge, you know, it's something that I wanted to do for a long time now, just the Kaggle challenge. And when I saw that one, I thought that it was a very interesting challenge, you know, and I decided to spend some good time on doing it. Yeah, so for the last 3 months or 4 months or so, I've been partnering with a colleague of mine that is living in Berlin in Europe. And we are working on several different projects. Some projects related with satellite imagery and using deep learning algorithms in order to detect different crop types and yield of agricultural fields and so on. We are working on a personal website, on a website that aims at answering questions based on scientific articles only. It's still work in progress, but we expect to publish something more or less soon. So I will let you know when this is done, Alex.
Yeah.
That's basically it. Just working on smaller projects. I might start a collaboration with people at the university here as well. Also in some project related with satellite data. I mean, images taken by satellite. And that's basically it. Nothing fixed, but involved in many small, interesting projects.
That's nice. Now, one question arises me. Would you say this challenge would have been possible if you were working in a 9-to-5 office job?
No, I wouldn't have been capable of doing so well while working 40 hours a week. I would have had to spend like every night and weekends working on this, and this is not something that I'm willing to do.
Yeah.
So I could do this basically because I had a lot of free time.
I'd say that's important.
But I think that this is something that applies only to this particular Kaggle challenge. I think that, I mean, I haven't taken part in any other Kaggle challenge actively, or I have not been as important as in this one, but in other cases, the best solutions are based on, yeah, sure, you first need to understand the data first, but then people in general develop deep learning algorithms that are based on architectures that are already out there, you know, and just making small making small modifications of these architectures that are already there. So I do think that you can finish in a pretty good position in a Kaggle challenge, and even winning a Kaggle challenge without a lot of involvement. The only thing is that in this particular case, in this particular challenge, you know, you really started from zero in a field that is completely new.
Yeah, crazy.
Mm-hmm.
Okay. So next question would be, what gave you an advantage in some interview or to get some position? What would you say was important?
I would say that just my education has been in general good enough to get into the positions that I've been working at. Like my first job, just the people who were hiring me, you know, just knowing that I had studied mathematics and physics seemed to be more or less enough. And in one interview of just some normal chatting, you know, we understood each other well, and that was it, you know. And that was my first job, so I was very happy that it happened this way. It seemed to be easy. And then for my next job, basically it was important that I had some, I mean, obviously my education as well, you know, knowing some mathematics and physics, whatever, but also having some programming experience was also valuable, you know, like knowing how to program in C++ or in Python, you know. Sure, it's something that many people know how to do, you know, by now, but it's something very valuable. It's something that many people know how to do if you are in the field of data science in general, or if you have studied software development, for sure, you know, or computer science, for sure, you know, but amongst mathematicians or engineers, it might not be that common. And in the end, it's very useful. And then when I came to New Zealand, I did look for a job, you know, sometimes. It was complicated because of the pandemics and so on. But after completing the Kaggle challenge, I included it in my CV. And in many of the interviews, people who were interviewing me, they didn't care that much about my education or experience or whatever, you know. And half of the time we thought, oh, it's so cool, you know, that you finished this Kaggle challenge and finished second. Oh, that's so nice. And one of the interviewers even had finished in a very good position in a Kaggle challenge himself, you know, so he felt very identified with me, you know. So that was quite cool.
Yeah, side projects can be important, more important sometimes, depending on the result. But
yeah, I think in the end, one of the things that is very important is to have some sort of connection with the interviewer, you know, and in the end, it all goes down to luck, you know.
yeah.
Oh, well.
Yeah, chemistry.
Yeah.
It has to happen.
It has to happen.
Yeah. What lessons did you learn along your career?
What lessons have I learned?
Something that changed your mind, your views.
Yeah, I don't know, many things, I guess. One of the things that I can think of right now is that I have been working for MathWorks until very recently, right? And MathWorks is a very big company. You know, there are like 5,000 people working there. Like software developers, it's like 2,500 people. And in the end, you're contributing to a huge and immense code base. And one of the things that I learned that surprised me a bit, you know, was how useful it is to develop code that is well written and readable. And and that, you know, whenever you went into any file, you know, and read the code, you know, you could understand everything easily. Nothing was cryptic, you know, everything was, you could read it like a book, you know, in order, and you would understand every single step of what was going on, you know. And I found that very useful because you didn't need to go and ask other people, hey, what does this mean? What does that mean? You know, and so on. And this is something that surprised me a bit, you know, because when you are studying or when you are doing programming for yourself or whatever, or when you are doing your own projects, it's something that you don't care about because, you know, it's your code, you already know what it's doing, right? So
You think so?
So yeah, you think so, yeah. Yeah, you think so. And in the end, you know, if you write good code and you go back to it after 1, 2, 3 months or 1 year, it if it's written in a not nice way, you will not understand what it does, even if you wrote it, right? So
Who wrote this shit?
you wrote this shit, yeah. So really, I understood the value, you know, of writing high quality code.
Yeah, if you don't care about other people, at least care about your future self. Be nice to him. Yeah.
Yes.
Okay. Do you have an anecdote along your career, or?
Well, when I joined MathWorks, one of the funny things that happened at the beginning was that on the first day at MathWorks, they assign you a buddy, which is the person that you are going to be working most closely related with, and he's kind of in charge of showing you a bit how the company works and answering you any questions if you need to. And you're basically talking to him like 1 or 2 hours every day during your first 2 or 3 weeks, you know. So I went into MathWorks, I met my buddy, you know, and after chatting a bit with him, I found out that he had been a flatmate for 4 years of a good friend of mine that had been studying at university, you know, whereas there had not been any connection at all, you know, between me and him in terms of location or universities or nothing, you know. So in the end, you know, it's an example of, you know, small world, you know, like how you find connections so easily amongst people that are doing similar things to what you are doing.
Yeah, that's exactly the same thing that the last guest told me, like realizing it's a small world in niche. Yeah. Okay. Any other things? No. Okay. Okay. Yeah. What achievements would you say you never imagined before when you were a student?
Achievements at a professional level. Um, I don't know. To be honest, when I was a student, I didn't really think that much, and I have never really thought that much of, you know, what I want to become in the future, or I haven't had any particular goal, you know, like I want to do this, I want to do that in the future, I want to be that good or whatever, you know. I've kind of been doing whatever I felt like doing at every point in time, right? And I've been just going step by step, and it has been working well. Sure, I mean, joining a big, nice company, you know, in a country that is not my country, you know, like when I joined MathWorks, it's a nice achievement, you know, to join such a nice team.
Yeah.
Finishing second in the Kaggle competition is a nice achievement as well. But it's not that I didn't expect, you know, like it's not that I consider that I did more than what I would have expected to achieve, you know. It just happened, you know.
So you maybe enjoy the process more than the prize.
Yeah.
Yeah, that's good, because if you enjoy the game, you have more patience, and whatever comes is good.
Yes. It also means that you don't have any too high expectations that in the end put some pressure on you, and then I don't know, if you don't achieve these expectations, then it might be mentally damaging. I don't know.
Yeah, that's good. That's a good insight about expectations. About data science, now or short term, long term, it doesn't matter. What trends do you see?
I mean, right now, the trends are already going towards deep learning in general a lot. You know, everyone starts doing deep learning for more and more applications. People, like researchers, are finding out about more different deep learning architectures. You know, like, I mean, there have been in the past few years, as I said before, you know, like CNNs, LSTMs, recurrent neural networks, GANs are becoming very famous, you know, lately, and many architectures that are out there, you know, and that are new and that can be applied to many different domains. So I would say that this is the big trend right now, you know, like how to apply deep learning algorithms to every different sort of problem that is out there. Is this good or not? I don't know. In the end, I think that whenever you want to solve a task, you need to understand very well what this task does. And whenever you use a tool, whenever you use an algorithm, you need to understand very well what this algorithm is doing inside, you know, and what this algorithm is good for and what not, you know. And I see many people just trying out random things within deep learning in neural networks, you know, like, yeah, let's try a convolution here, an LSTM layer there, just to see what happens, without really thinking about why, you know, why am I using this architecture, you know, what is the usefulness of that? Why am I using a deep learning algorithm and not some other deterministic algorithm or another machine learning algorithm that actually makes more sense to use, you know? So yeah, sure, deep learning has helped. In many ways, it is improving the performance of many algorithms that were out there before, you know, for solving many different tasks, but one needs to be aware of what the algorithms are actually doing, you know, and what they are used for, and whether your application is the good one, you know, for the usage of a deep learning algorithm.
Yeah. Can you combine perhaps more like the algorithms that you know very well what they are doing with some pieces of machine learning?
Yeah, sure. Again, you can combine anything you want, you know, as long as you do it with a purpose, as long as it makes sense, I think.
In fact, I would say your solution does that.
Probably, yeah.
Because it's like an algorithm and some of the transformations happen to be machine learning or deep learning.
Yeah.
So, yeah. And on a more philosophical note, because you were mentioning all these advances consisting of just new architectures of deep learning, François Chollet criticizes that on the paper and says that it's not learning, it's just knowledge about the task encoded in the architecture of the neural network.
Mm-hmm.
I know. How does that? Yes, go on. You were saying.
It's true and not, no, I think, again, I think that the concept of learning as well as the concept of intelligence, you know, is different for algorithms than for humans, I think, right? And again, what does learning mean, you know? Yeah, sure, the algorithms are learning the parameters, you know, based on examples, right? And I don't know, that's what it is, you know, the architecture in the end, what it does is like it determines how the parameters interact with each other and with the inputs, you know, and you need to organize your architecture in a way that makes sense given the structure and the meaning of your inputs.
Yeah. Okay. So next question would be, what's your next goal for now?
So as I said before, I'm involved in several different projects, right? I look forward to working on all of these projects, but in particular, I look forward in developing this question answering algorithm or website that I told you before, because it's a personal project that we are developing with a friend of mine. We are basically doing more or less in our free time, meaning that nobody is paying us for doing it or anything, you know, it's just for fun and because we think it's something good, right? So my next goal that particularly motivates me would be to have some sort of service that is actually useful and that works well and that can be used by anyone who wants it, you know. Let me explain a bit more what it is about, if that's okay.
Yeah.
So it's about question answering, as said. This means that the way the website would work is that you as user would type a question, and then we have a huge data set of abstracts of scientific papers, basically all of the PubMed abstracts. So it contains all of the research that has been done ever in the field of biomedicine, biotechnology, all that stuff, right? So our algorithm, given your question, it would look for an answer in all of the PubMed abstracts. And then it would give you like a set of different answers, and it would link you to the research where these answers are given to your question, right? So if you have a question, not only will we answer your question, but we will also give you the scientific reasoning behind the answer.
Pointers.
Yep.
Nice. So the end user would be a researcher.
Basically, yeah, but not necessarily only, you know, anyone could ask questions.
Yeah.
But yeah, probably researchers would find it more useful than other people.
And how do you train it? How does it learn?
So right now we are just using pre-trained algorithms. There are pre-trained deep learning algorithms out there that have been trained specifically for the task of answering questions. There is this by now quite famous Python package called Transformers by Hugging Face. They have a lot of natural language processing related models, and in particular, they have question answering models. They have, the models are called, like BERT is very famous. It was kind of the first one, I think, from back in 2017, 2018. And then some other models have developed out of there, you know, in different languages, making the algorithms small, like the networks smaller or faster and whatever. One of the problems that these approaches have right now is that the networks are huge, you know, like the model that we are using right now, it has 66 million parameters inside, right? So in order to answer a question, you need to have very powerful software in order to answer it quickly. So one of the challenges that we have is how to ask as many questions as possible in an efficient way, which is not easy given that the algorithms are very time and computationally expensive, you know.
So like multiple users handling multiple requests efficiently, you mean, or training it?
That's one thing, but another thing is, hey, I want to answer a question, but I have to ask this question, the same question, to many different abstracts. The more abstracts I consider, the better, the more reliable my answer will be.
Okay. And you have to choose which ones.
Yeah. Yeah. And right now we selected extracting some keywords from your question.
Okay, some statistical information.
Yeah.
Okay. Yeah, I hope it works out.
Yeah, we'll see. Working on it.
Yeah. So finally, the last question is, what advice would you give to someone starting their career?
Like deciding how to study. Well, yeah, whatever. I would just tell someone that is starting their career in data science that, hey, just data science by now, machine learning, deep learning, whatever, is applied in many different fields. So go ahead and choose wisely. Choose whatever job or whatever direction you can relate yourself with. Choose an application of data science and of deep learning that you think is good for the world, and that motivates you, and that you think that you can make a good contribution. You know, choose a project that motivates you, basically.
So if you love horses?
Horses.
Horses.
I don't know. I'm sure that there are things related with horses. You know, I can think. I don't know. My wife, she's working on genetics, right, of endangered species. So she's working on animals. She's studying the DNA of birds. You know,
New Zealand.
So, yeah, in New Zealand. Yeah. So, and she's basically programming, you know, and doing statistics and so on. So, yeah.
Okay, and for example, about you, what do you find motivating?
Me, I don't know. I'm always happy to be involved in any sort of project that I think contributes positively to society and can help people in some way.
Yeah, you can have said that. Yeah. Okay. Yeah. Then this will be it. Next, I ask you to give us a source of knowledge or some book or some website that you find useful, if you have it thought about it right now, or if not later.
I was thinking of recommending this book called Weapons of Math Destruction.
Okay.
It's written by some mathematician that was working in the past for a couple of companies and has seen or has thought of and has studied how deep learning algorithms or machine learning algorithms contain a lot of bias in their data, you know, and raises an alarm as of, hey, we need to be very, very, very careful as of how we build our algorithms, because in the end people are going to be using them and they do not know which data has been used in order to train them and so on. So I think it's very important to be aware of the potential problems that an algorithm that you train might have.
How do you solve that?
Probably you would need some legal tools to avoid some injustices to happen.
Legal tools.
Yeah.
Okay. I mean, I don't know if I understood your answer. How do you combat bias in algorithms?
I mean, I meant bias that has a direct or indirect impact socially in people in real life, you know, that they get discriminated because this algorithm doesn't consider a person fit for whatever, or because the algorithm considers that a person, because of your I don't know, age or background or race or whatever, you know, more likely or less likely to do something or have more money or whatever, you know. So yeah, that's what I meant.
Yeah, so the question was how do you solve that problem? Because you train it on data. If the data has bias, okay, what do you do?
I don't know, but you, in certain cases, you need to avoid at all costs, you know, that some bias has an impact that can be negative for some people just because. And when I said that maybe the solution is legal tools, I mean, that's what I meant, you know, like having some laws, no, really having some laws out there that make some algorithms like illegal or whatever, you know, that do not allow this to happen, you know, because right now, if this happens, probably why is it the case, you know, why does it happen? Because sometimes, you know, just training an algorithm, you know, you just give it some data, you know, you train and you have something that gives you an output that is more or less okay, you know. It's just cheap to do it this way, you know, and it's cheap and easy. You have some data, you train it with this data, gives an output, perfect, you know. But probably there needs to be some thought given, no? There needs to be some study happening and going on as of, in order to understand really what the algorithms are doing, right? And whether it's impartial or not really. And this is some money and effort that I understand that people are not willing to put, you know, in some cases.
So the developers should understand the algorithm, or also the users should understand the algorithm.
Yeah, probably the developers, or maybe not the developers, but whoever is in charge of distributing the algorithm or the software has to make sure that it accomplishes a certain set of requirements.
Okay. Yeah, okay, I think that's it. And the next step would be, where can we find your work or some personal project about you?
Yeah, I will just share you my GitHub.
Yeah, that's where the...
It basically contains the code for the Kaggle challenge, but maybe I will start uploading some other things.
Yeah, load it with everything you have. Okay, and later, if you can think about someone to interview next that you know, that would be nice. 1 or 2 people.
Yeah.
Okay. Yeah. Okay. So that was it. Thanks for coming in. I hope we all learned something today. And yes, that's it. Bye bye.
Thank you very much.
Bye. See you soon.